All right, let's dive in. Today, we're going to be chemical detectives. We're cracking the code that chemists use to figure out the invisible world of molecules, turning what looks like just a bunch of numbers into actual, real life chemical formulas. So, here's a question for you. We all learn in school that water is H2O, but have you ever stopped to wonder how we know that? I mean, you can't see a single water molecule. How on earth did someone prove it was two hydrogens and one oxygen? It definitely wasn't a lucky guess. No, it was a process, a logical deduction, and that's exactly the process we're going to unpack today. To answer questions like that, you can't just wing it. You need a very specific set of tools. So that's what we're doing here. We're going to build that toolkit together, piece by piece. By the time we're done, you'll be able to think like a chemist and decode the formula of pretty much any compound that comes your way. Okay, so here's our game plan. First, we're going to figure out how to weigh a molecule. Then, we'll find its most basic recipe. After that, we'll uncover its true identity. And finally, we'll learn the grammar that makes chemistry work. Let's get started with that first tool. First up, weighing the invisible. Seriously, how do you weigh something you can't see, let alone put on a scale? Well, chemists came up with a really clever workaround. It's all about comparison. And that workaround is called relative molecular mass, or RMM for short. Now, the key thing to get here is that this isn't a weight like grams or pounds. It's more like a score. It's a relative number, totally unitless, that we get by simply adding up the relative atomic masses, the scores, of every single atom in the molecule. Let's do one together. We'll use calcium carbonate, CaCO3. So step 1, we list out our atoms. We've got 1 calcium, 1 carbon, and 3 oxygens. Easy enough. Step 2, we look up their scores, their relative atomic masses, on a periodic table. Calcium is 40, carbon is 12, and oxygen is 16. Okay, last step. We just do the math. We've got 1 calcium at 40, plus 1 carbon at 12, plus 3 oxygens, each worth 16, which is 48. So what does that give us? Boom! A perfect 100. The relative molecular mass of calcium carbonate is 100. See? Simple as that. And this number, this is a really fundamental piece of our puzzle. So, now that we know the total score is 100, we can break it down even further. How much of that 100 came from the calcium? How much from the carbon? From the oxygen? Answering that gives us what's called the percentage composition. And here's what that looks like. It's super clear, right? Calcium gave us 40 points out of 100, so it's 40% of the mass. Carbon gave us 12, so that's 12%. And those 3 oxygens pitched in 48, making up the last 48%. This kind of data, these percentages, is often the very first clue a chemist gets when they're trying to identify a mystery substance. All right, tool number 2 for the toolkit. Now we're going to get really clever. We're going to flip this whole process on its head. Imagine you're in a lab and an experiment just gives you the percentages. How do you work backward from that to find the formula? Let's find out. Okay, first, we've got to get 2 terms straight to avoid any confusion. The first thing we're going to find is the empirical formula. Think of this as the basic recipe. It's just the simplest ratio of ingredients. Later on, we'll find the molecular formula, which is the real recipe, the one you actually use. Exactly. The empirical formula gives us that fundamental building block. It might not be the whole picture, but it's the absolute most important first step in figuring out what an unknown substance actually is. Okay, let's put it into practice. Imagine an experiment tells you that some mystery powder is 43.4% sodium, 11.3% carbon, and 45.3% oxygen. Our mission, as you can see here, is to turn those percentages into a simple chemical ratio. Here's how we do it in 4 steps. First, we have to turn percentages into a count of atoms. Now, chemists use a unit for this called the mole. Don't let the word scare you. Just think of it like a chemist's dozen. It's just a standard amount for counting something unimaginably tiny, like an atom. To get the mole ratio, we just divide each percentage by its atomic mass. Okay, step 2. To get the simplest ratio possible, we look at all our results and divide every one of them by the smallest number, which in this case is 0.94. And what do you know? That gives us a beautiful, clean, whole number ratio. 2 for sodium, 1 for carbon, and 3 for oxygen. And just like that, we've got our empirical formula, Na2CO3. But wait, is that the final answer? The real formula? Well, not always. For that, we need our third tool, the one that uncovers the molecule's true identity. And this is where the molecular formula swoops in. It shows the actual number of atoms, not just the simple ratio. And the key is this powerful little equation right here. It says the mass of our empirical formula, our basic recipe, multiplied by some whole number n, has to equal the RMM of the actual molecule. Okay, final boss battle. Let's put everything we've learned together to solve this one mystery. We've got a hydrocarbon. That just means it's made of hydrogen and carbon. We know it's 80% carbon by mass, and its total RMM is 30. Your job? Find its true formula. Let's go. Step 1, you guessed it, we find the empirical formula, that basic recipe, just like we did before. If it's 80% carbon, while the other 20% has to be hydrogen, we divide each of those by their atomic mass to get our mole ratio. Then we divide both of those results by the smaller number, 6.67, to simplify it. And that gives us a really clean ratio of 1 carbon to 3 hydrogens. So our empirical formula is CH3. Now for the final reveal. Let's get the mass of our basic recipe, CH3. That's 1 carbon at 12, plus 3 hydrogens at 1 each, which gives us 15. Okay? Now remember, the problem told us the real RMM is 30. So, using our magic equation, 15 times some number n equals 30. Well, that means n has to be 2. So we just multiply our empirical formula by 2, and we get our final answer, C2H6. That's ethane. We did it. We cracked the code.
Awesome. Okay, we have just one more tool to add to the kit. Once we know what molecules are, we need to know how to describe what they do, how they interact. This is where we learn the grammar of chemistry, balancing chemical equations.
Take a look at this reaction. Aluminum plus chlorine gas makes aluminum chloride. If we do a quick head count of the atoms on each side, we run into a big problem. As you can see, we start with 2 chlorine atoms on the left, but we end up with 3 on the right. Uh-oh, that can't be right. You can't just create atoms out of thin air. This equation is unbalanced. It's bad grammar. Now, to fix this, there is one golden rule. We can only change the big numbers that go in front of the formulas. These are called coefficients. We can never, ever change the little numbers inside the formulas themselves, like that 3 and AlCl3. That would change the actual molecule. So by strategically putting a 2 in front of the aluminum, a 3 in front of the chlorine, and a 2 in front of the final product, everything clicks. Now we have 2 aluminums and 6 chlorines on both sides. The sentence is balanced, the grammar is correct. And there you have it, your complete chemical code cracking kit toolkit. We learned how to weigh a molecule using relative mass. We saw how to work backward from lab data to find a compound's simplest formula and then its true formula. And finally, we learned the rules for writing balanced chemical reactions. You now have the fundamental logic, the exact thought process that chemists use every day to identify new things and understand the world on the deepest level. So the real question is, now that you have these tools, what chemical code will you go out and crack next? Thanks for tuning in.